Okay, guys, broadcasting the solutions to Lab 5.1. All right, number 11. Refer to your pre-lab notes, which you don't have, and write the balanced reaction for this lab equilibrium. Okay, so that was 2 NO2s gas were in equilibrium with 1 dinitrogen pentaoxide gas. Indicate the color of the reactant. Okay, this was dark brown. The product, this was clear, and the color at equilibrium, that was light brown. Write the Kp expression. Okay, so Kp is going to be equal to products over reactants raised to the power of the coefficient. Notice we only have one coefficient in here of 2, so that's going to be the product, N2O4 divided by the reactant, NO2 raised to the power of 2. Because this is a Kp problem, when we ultimately are going to start doing calculations with these, this is going to be in atmospheres. Okay, moving down here to 13, tells us that the Kp value is less than 1. Okay, so if Kp equals reactants over products, and that value is less than 1, we can think about it metaphorically as kind of like that. Ooh, I'm sorry. Kp equals products over reactants. A large reactant value and a small product value is going to give you a equilibrium that is reactant heavy. Sort of explains why initially the reactant was dark brown and the equilibrium color was light brown. These two had more in common than these two. Based on your answer below, is the reaction spontaneous or not? So we know that delta G equals negative RT natural log of K. And we know if K is less than 1, then the ln of a number less than 1 is a negative number. If you pop in a negative number here, delta G equals negative RT of a negative number, you're going to get a delta G that's going to be positive, and therefore it's going to be non-spontaneous in the forward direction. For 15, it's actually asking us to calculate the value for delta G. So I'm going to set it up as usual, and you can plug those numbers into your own calculator. Delta G equals negative R, 8.314. It's important to remember that R for equilibrium is 8.314, and R for gases equals 0.0821. We're not using this one here, we're using this R. Times T, 25 plus 273 is 298 Kelvin. Ln of K, and I believe K is, in this case, I got to relook here, 0.012. So we know that this number is going to be positive. We don't know what the number is, but the units are going to be kilojoules per mole. So you guys can go ahead and plug this into your calculator and get the number and put it right there. Setting up the calculation is really the most important thing on a free response problem. Okay, what color was favored when the temperature was increased? Okay, that was dark brown. And that was a left shift. Okay, what color was favored when the temperature decreased? Okay, that was clear. And that was a right shift. Based on your answers to 16 and 17, is this reaction exothermic or endothermic? Okay, it's going to be exothermic, and here's why. If you have the reaction, 2N2 gas is at chemical equilibrium with 1 dinitrogen pentaoxide, and it's exothermic, that means temperature is on the right side. You increase temp, it's going to shift to the left, okay, up, and away, and this was the dark brown side. If you decrease temp, it's going to down, stay, and this was the clear side. And that's exactly what was observed. When temperature was increased, dark brown occurred, and when temperature was decreased, we saw the clear. I want you to skip this. Go ahead and skip this problem. Go ahead and skip this problem. Go ahead and skip this problem. Okay, these all have to do with pressure effects on equilibrium, and I did this with blocks 5 and 6, but I did not do it with blocks 2 and 3 towards the end of the day because we needed to finish up the lab. So we'll go over this later. If you're in blocks 5 and 6, feel free to try and answer these questions if you like. 22, we have a mixed gas problem. So I'm saying you have that little bulb right now, and I'm saying inside this bulb you have 0.50 grams of NO2, and you have 0.50 grams of N2O4. And I'm asking for the total pressure. So we know that the volume and the temperature and R inside this bulb are going to be the same. They're asking for total pressure, which we don't have, so we can't use equation 2b. We're going to have to use equation 2a. Remember that this is a mixed gas problem. Okay, we have two gases. So we're going to use P total is going to be equal to the sum. Remember 2a, which is P total equals PA plus PB, etc. can be reduced to this. N NO2 plus N N2O4 RT divided by V, and we're going to plug into this equation. But the first thing you need to be able to do is you need to convert these to moles and then plug them in here. So 0.50 grams of NO2, okay, NO2, this is 32 grams, this here is 14, so 32, is that right? Okay, so that's 46. So 46 grams per every 1 mole of NO2. That's going to be what goes right there. And for 0.50 grams N2O4, okay, 4 times 16 is 64, plus 28 is 92. 92 grams of N2O4 for every 1 mole. And that is going to go there. Okay, so now we did both of these gram to mole conversions and plug those in to get moles of each. We know that this is going to be 0.821. We know this here is 298, and we know this here is going to be liters. We're going to have to divide those 20 milliliters by 1,000. You're going to get a really big number, some like 19,000 ATMs or something like that when you do it out. Now it's going to seem ridiculous, but this makes a lot of sense. 20 milliliters is a really small space, and 0.5 grams, that's 1 gram of each of these gases in that small space. I did make these numbers up, that's why it's so large. In retrospect, I probably should have made this 0.05, but you know, this is a very, very important calculation to be able to do. So let's look at it again. We have a mixed gas situation. Okay, we are asked for P total. We have the same V, we have R, and we have T. Therefore, we convert both of these to moles, and we plug those moles into the balanced equation, and we're good. 23 says if a small hole is poked in the pipette bulb, okay, so here's the bulb. Inside it you have NO2, which we found out up there weighs 46 grams per mole, and you have N2O4, which we know weighs 92. If a small hole is poked, which one would diffuse faster? So we know with the fusion, if you look at equations 4a, the lighter one is faster. So NO2 is going to get out first. Okay, so NO2, it's lighter, and there's a square root involved. So the square root of the molar mass of N2O4 divided by NO2, which is going to end up being the square root of 2, is how many times faster NO2 is than N2O4. Okay. Hope this podcast was helpful. See you later.